Okay, so we start today the thin layer chromatography. Now, the thin layer chromatography is exactly like the paper chromatography, but it has two differences. That in paper chromatography, we usually use a sheet of filter paper or a cellulose paper, and we said that the mode of separation here, how the components in a mixture separate, it depends upon the solubilities, the different insolubilities of the solute between the mobile phase and the stationary phase. We said that we have a stationary phase, which is the phase that does not move, and the stationary phase here is the filter paper. And we said that the filter paper contains holes, and these holes are filled with water. It's in its constituent, in the cellulose paper itself. It has holes containing water, trapping water inside it. Although if you feel the paper from outside, you don't feel it wet. It's dry, but inside its pores, there is water. And we have the mobile phase, which is a solvent, an organic liquid. And so the solution, the solute will partition itself between the water in the stationary phase and the organic solvent that is moving as the mobile phase. And this is the mode of separation. It depends upon the solubility of the solute in the water and in the organic solvent. But in the thin layer chromatography, our stationary phase is going to be a piece of glass or a piece of plastic, either a solid material like a piece of glass or a piece of plastic. And then we make what we call a slurry. We make what we call a slurry of alumina. This is alumina, which is the aluminum oxide, or silica, which is silicon 4 oxide. We make a slurry with water. You know what's a slurry? It's when you add something to water, but you don't put water too much. So here we have a solid, and here we have water, and this solid does not dissolve in water, and you make a very small amount of water over it, and so that's what we call a slurry. It means that the solid did not dissolve in water. You know, ajina. You know what's ajina in Arabic?
Yes, yeah.
Yes, something like that. So the solid does not dissolve in water. It forms only a slurry with water. And so we get this slurry of either alumina or silica, and we put a layer over the plastic sheet or the glass sheet. And this layer should be very thin. That's why this method is called thin layer chromatography, because the layer at which the separation will take place is very thin. It's a thin layer chromatogram. Okay, so we put a very thin layer of alumina, which is formed in the form of a slurry, or silica, and these are white in color. So our in front chromatogram is white in color. And then they put it in the oven so that it gets hard. And this is how do we make a thin layer. And then, like in paper chromatography, the same technique, using a pencil, we are going to put here a baseline using the pencil, and using a very thin capillary, we are going to put the mixture of solutes. Of course, the mixture should be put at the baseline, but I don't know why they are drawing it here, but it should be on the baseline at the beginning. And then we place this thin layer on a beaker containing water or containing the solvent that we are going to make our separation using it. And we cover the beaker with a lid. Okay. And here the mode of separation, here depends on two things. Depends on the solubility of the solutes in the mobile phase, and also depends on the adsorption on the surface of the stationary phase. Okay, So it depends whether the solute would like to move with the mobile phase. When it likes to move with the mobile phase, this means that it is more soluble in the mobile phase. It likes to be soluble in the mobile phase, and also depends that other solutes would like to be adsorbed. Adsorbed means to be placed at the surface, not to be absorbed, but to be adsorbed at the surface of the stationary phase. It's going to be absorbed at the stationary phase. Of course, if here alumina and silica, they are polar. And this means that our stationary phase is polar. And so the solutes that are also polar, because we said before that like dissolves like, everything would like to go with what resembles it. So if we have a polar solute inside the mixture, so the polar solute would like to be adsorbed at the polar alumina or silica at the surface of the stationary phase. But if it's not polar and it would like to dissolve more in the mobile phase, then it's going to move with the mobile phase. And by this way, they are separated from each other. The solutes that would like to be adsorbed more than to be soluble in the mobile phase will stay retained, while the solutes that would like to be soluble in the mobile phase, they are going to move with the mobile phase and go upward. And also we wait until the solvent comes near the end, and we take the thin layer outside, and we put, using a pencil, we are going to put the solvent front. And also either our components are colored so we can see their places, or else we can spray them with a locating agent to determine their positions, and we calculate the retardation factor of each solute from the other. We can calculate the different retardation factors, and from which we can determine our components from reference books. Okay.
Miss, I have a question here. This mode of separation applies to all chromatography, even the paper, right?
No, for the paper, we only said solubility. I told you at the beginning. In case of water, it depends on solubility. In case of paper chromatography, it depends on solubility only. Because whether the solute would prefer to dissolve in the organic solvent or to dissolve in the water that is trapped in between the holes of the cellulose paper. It is not adsorbed. Here it is soluble. Understand?
Oh, okay. And Miss, for the thin layer, the more the solubility and the less the adsorption, it means the higher it will travel in the paper, right?
Yes, it means the higher it will go up with the mobile phase through the thin layer.
Yeah, okay. And also, Miss, I remember in school we solved question 2B and I didn't understand it. So can we solve it?
A mixture of propanone and hexane was separated on HPLC chromatogram using alumina as the stationary phase and methyl benzene as the solvent. Which substance would you expect to rise further up the chromatogram? Now, as I was just telling you now, that this alumina is polar. Yes, alumina is polar. It contains aluminum ions and oxide ions, so it is a polar stationary phase. So what will absorb on the surface of the polar surface should be a polar solute. Okay?
Yes.
Because like dissolves like. Now, if we look at propanone, propanone is polar because propanone is CH3, C double bond O, CH3. And this means that oxygen carries a partial negative charge, carbon carries a partial positive charge, and it's polar. But hexane is non-polar, isn't it? It is an alkane, and all alkanes are non-polar. So if we have a mixture of these two, one of them is polar and the other is non-polar, and we run this mixture on a TLC chromatogram containing alumina, which is polar. So which one will be absorbed at the surface of alumina? The polar one, because we said that like dissolves like. Since alumina is polar and propanone is also polar, so propanone would like to be absorbed at the surface of the thin layer paper, thin layer. But hexane would like to move with the mobile phase because the mobile phase is non-polar as well. It is methyl benzene. And we have a methyl group, so all of it is non-polar. All of it contains hydrogen and carbons. And this means that methyl benzene solvent is non-polar. So hexane, which is also non-polar, will move with the non-polar solvent. But propanone, which is polar, will stick or be absorbed on the polar alumina.
Oh, okay, fine.
Okay.
Yes, I got it.
Now we come to a third method in chromatography. We call it high performance liquid chromatography, or sometimes it is called high pressure liquid chromatography. Either we say this pressure or we say high performance. So let's call it high performance as it is known here in this book. Now, what is high performance liquid chromatography? We bring in high performance liquid chromatography, we bring a column, okay? And we are also going to fill this column with silica or with alumina, and these two have very, very fine particles, okay? So this is the column that we are going to fill. We are going to fill it with very fine particles of either alumina or silica. And of course, when I say very fine, it means that they are in the form of a powder, which is very, very fine particles of powder. Okay, so we are going to fill this tube with this very fine particles of alumina or silica, and we are going to pass our mixture through this column in order to be separated, of course, using this is the stationary phase, which is alumina or silica. It is the stationary phase. And usually also we are going to use an organic solvent as the mobile phase. The mobile phase is an organic solvent. Okay. Now, if we want to pass our mixture or our organic solvent through this column, it's very difficult. Imagine that you are filling a cup at your home with flour. You know that the flour has very, very fine powder particles.
Yeah.
If you try to pass water through it, it would be very difficult because the very fine particles here are strongly packed and strongly adhering to each other, not leaving any spaces for water to pass through, isn't it?
Yeah, true.
And the same is here. If we are packing this column with very fine particles like the flour, it resembles the flour with alumina or silica, then this means that it will be very difficult for us to pass either the mobile phase through it or our mixture. That's why here we use pressure. That's why at the beginning I told you that sometimes it is called high performance liquid chromatography, or else we call it high pressure liquid chromatography, because we have to use pressure in order to force the mobile phase and our mixture to pass through this column. Okay, so here, as we said at the beginning, we got this column, we filled it with very fine particles of alumina and silica, and we are going to put our mobile phase here in a reservoir in a certain container, and then the solvent delivery system, this is the pressure that we are going to apply. We are going to use a pump in order to pump the mobile phase from the container or from the reservoir and letting it be mixed with our mixture. The mixture, which contains, for example, 3 components, A, B, and C, is going to be injected here. And then using the pump, the mobile phase is going to be mixed with our mixture and forced to pass through this container, through this column. that contains the very fine particles of alumina or silica. Okay. And also here we find that alumina or silica, they are the stationary phase, it is a solid. And so here also the mode of separation will depend whether the solutes in our mixture would like to prefer to be soluble in the organic solvent and move with the organic solvent, or would like to be absorbed at the surface, because alumina and silica are polar. If our component is polar, this means it would like to be absorbed on the surface of alumina or silica more than to move with the liquid phase, which is the mobile phase. And then we are going to connect a detector to this column in order, because every solute comes out if we have A, B, and C. If A would like to be more soluble in the mobile phase than to be absorbed at the surface of alumina, then it will move with the mobile phase, and it will be the first one to be detected using the detector. Here is the detector that is going to detect the presence of every solute particle in the mixture. Okay. And here we are going to find out what we call the retention time. We have something that is called the retention time. What is the retention time? The retention time is the time that starting by injecting here our sample, we are going to record the time starting from here. So the time required for the solute to be injected and then to be detected by detector, here we call it the retention time. It is the time counted for every component. Of course, when we inject our mixture here, when we inject it here, we record the time. We start a stopwatch. And the detector, of course, we do not start a stopwatch, but the detector will detect when did we injected our sample. And then when A comes out from the column, the detector will detect its presence and calculate the time required for A to, from the time it is injected to the time it came out from the column. The detector will detect this. This is the time detected. Of course, A came first. The time is 0 here, and it becomes bigger and bigger as we go to the right-hand side. So when A came outside from the column, the first one, then it is detected. This is its retention time. And B came next with a certain retention time, and C was the last one to come out. So its retention time is the greatest. And of course, the area under each peak is the concentration of each component in these solids. Okay, understand, or shall I repeat it?
Miss, my question here is for the mixture that contains A, B, and C. Shouldn't it be placed in the packed column and then the organic solvent would come?
Yes, that's what they did. But they put an injector here to inject the sample. Instead of injecting it here, it is injected here, so that it will be mixed with the organic solvent, and the pressure here would push them together to pass through the column. Because as I told you, if they are not pressed, if we do not apply a pressure, they will not pass through the column because of the very fine particles of alumina. So we have to push them in order to move inside the column.
So you have like an injector that contains the ABC, and where do you inject it from?
The injector is place where you inject your sample in. It is the place where you inject your sample in. Okay. You know how to inject something?
Yeah, miss, I just don't know, like where is it getting injected, and like
it is injected
can you draw
here. This is our sample. This is a container that we call it the injector. Okay. So we inject our sample containing the 3 components here. And in that place, it is mixed with our mobile phase. So to move them together through the column.
Oh, okay, fine.
Understand?
Okay, so you put both the ABC and the solvent in.
Yes.
You You put it in the injector.
Yes. This pump will pump the mobile phase from its reservoir or from its container. It pumps it here, and then it pushes the mobile phase to be injected here together with our sample containing the 3 components. And this pump would make it easier for them to be pushed and move throughout the packed column.
And Miss, here in this case, the alumina and the silica, they're both in the state of fine particles. But
yes,
in the other like thin layer, what was in it? What was it state? Like what was its state?
They are also fine particles, but in order to place a layer over this plastic or glass sheet, we made them at the beginning in the form of a slurry. I told you that a slurry means that we mix them with water. They do not dissolve in water. And we put a thin layer over this plastic sheet. And then we put it in the oven to get water away out of it, so as to leave it as in the form of a solid.
Oh, okay, fine. I got it.
Okay.
Yes, okay.
Now, where do we use HPLC? When do we use it? We use it in medical research to separate peptides and proteins. We use it to analyze samples of urine for athletes if they are taking something that is not legal to take it before they do their competitions. So they take a sample of urines from these athletes and they analyze it using the HPLC to detect whether the urine contains any compound that is illegal to be used in their competitions. Okay. And it is also used for monitoring pollutants in the atmosphere and rivers. We also take samples from rivers and samples from the air, and using HPLC, we can determine whether it contains something, because from the retention times, we can determine what solutes are present in our sample. Every sample will be separated as its retention time. Okay. So we can determine what are the pollutants that are present in rivers or in lakes or whatever. And also, if we have food, of course, ready-made food in our shops. And if they want to test whether this food is okay or does it contain something that is harmful to us, they also can take samples of this food and make the HPLC. Okay.
Yes, okay.
Okay. Now we have another kind of chromatography that is called gas-liquid chromatography. And in gas-liquid chromatography, the gas is the mobile phase and the liquid is the stationary phase. Now, at the beginning, we said that the stationary phase is the phase that is not moving. Stationary means it does not move, but mobile means that it is moving. Okay, so how can a stationary phase be a liquid? We said that we want something not moving, so liquids are, all of them, they should move. So how can we use them as stationary phase? So here in gas liquid chromatography, they use the column. You see, this is the column at which or through which the separation will take place. So here, this is our column that contains the stationary phase, which is a liquid. In order to let the liquid not move and be stationary, they use very columns with very small diameters. They are very small diameters, so as if the liquid is not moving. Either they do that, or they put what we call a solid support. So either they use, in gas liquid chromatography, either they use very fine columns in order separation will be done in it. And if we have very fine columns, then as if the liquid is not moving inside them because they are very fine. So as if the liquid is not moving, it is adhered between these two layers. Okay, it's very fine. And so the liquid, I can't draw it very fine, but as if the liquid is in between these two layers of the column and they are not moving. So either we do that, or else in the column, we put another solid support at which the liquid stationary phase would adhere to this solid support. Okay. And in this way, it will not move. Understand, Lara?
Miss, where do we place the solid support?
Excuse me?
Where do we place the solid support?
Inside the column. This is the place, the column where separation will take place. So we have to put the stationary phase here. The stationary phase is a liquid. So either we use very fine columns with very small diameters to put our liquid stationary phase in, so that it is as if it is not moving, or else we put a solid material inside here acting as a solid support for the stationary phase, which is a liquid. After we fill it with the solid support, we put the liquid, which is the stationary phase, and so the liquid will be absorbed on the solid support. Liquid will be absorbed on the solid support, and in that way, if it is absorbed on the solid support, this means that it is not moving. It will behave as a stationary phase. Okay, Lara?
Yes, okay, I got it.
Okay. Now, the mobile phase is a gas. And if the mobile phase is a gas, then our mixture should also be in the form of a gas, or else the gas will not be able to carry it through mobile phase. Mobile phase means that it carries the sample and goes by it through inside the stationary phase. So if our compound or mixture of compounds is not in the form of the gas will not be able to push it through the column. So that's why our components, our mixture, should also be in the form of a gas. So at the beginning here, as you see, the carrier gas or the mobile gas is put from here, is placed from here. Of course, the mobile phase, which is the carrier gas, should be inert, an inert gas, so as not to react with our components in the mixture. So we can use either nitrogen, or we can use argon, or any other inert gas. We are going to put it from here, and also we are going to inject our sample from this rubber septum here. You know what's a rubber septum? Sometimes when we take injections, sometimes the bottle containing the medicine, the bottle containing medicine has a rubber here. We call it a rubber septum. Yeah. And we put our syringe from here to suck the medicine into our syringe. Isn't it?
Yes.
So this is called a rubber septum. So here we are going to get our sample and inject it here in what we call a rubber septum that is found here at the beginning of the column. And as you see here, there is a port. This is called the injector port. And this port is placed in an oven, because we want to heat our sample so that it transfers to the form of a gas. Because as I told you, as the mobile phase is a gas, it cannot be able to move a liquid with it through the column. So our mixture should also be in the form of a gas. So how do we do that? We inject our aqueous solution or liquid or whatever through this rubber septum, and this rubber septum is placed in an oven so that our liquid or aqueous solution should be converted into a gas at once in this oven. And we are going to mix it with the carrier gas, and the gas will carry it inside the column to be separated. As you see here, all the gas liquid chromatography or this instrument, all of it is placed in an oven. This is the injector oven. This is the column oven. This is the detector oven. All of it is placed in ovens. Why? Because we want to be sure that always, all the time, our sample should be in the gas state so that the mobile phase can carry it through the column. Okay.
This here, the sample that is injected is the one that contains the components, right?
Yes.
Okay, and also can we say that in general, it's the solvent and the components must be in the same state?
Yes, they must be in the gas state, not any other state. They should be in the gas state because here our mobile phase is a gas. So both of them must be in the gas state so that the mobile phase could carry them through the column.
Yeah.
Okay, to be able to carry them through the column. Understand?
Yeah, miss, and this applies to also the other chromatographies. They have to always be in the same state, not necessarily gas, but
no. Yes, yeah, yes, okay, but here we are in high performance liquid chromatography. Our components are not liquids like the mobile phase. Maybe they are solids, but we dissolve them to be aqueous, but not liquid. So they mustn't be in the same phase.
Oh, fine, okay.
Okay, so now here what happens? The same. As the carrier gas takes our sample mixture throughout the column, then they are going to be separated depending on the solubility in the gas phase and the absorption on the solid material, or sorry, on the liquid stationary phase inside the column. As you see here, the column is too long because we are using our carrier, our mobile phase, a gas, and we know that gases take a big place. It needs a big place to be placed in. So instead of taking our column, a very, very long column, of course, it will take many rooms beside each other. So instead of doing that, they use the column that is a coiled column. As you see here, our column is coiled in order to provide enough space for the gas to be moving inside this column. And the separation will depend on whether our components or our solutes would like more to be moving with the mobile phase, which is the gas, or else to be absorbed at the liquid stationary phase. So if they are moving with the mobile phase, with the gas phase, they will come here. This is the place where the detector is placed. This is the detector oven, and this is the detector that will also here it will measure the retention time or the time required from the starting of the injection of our sample till the time where each component would come out in the detector. Okay. Understand?
Yes.
Okay, of course, here in case of the gas chromatography, gas liquid chromatography, the temperature should be adjusted because we know that if the temperature increases, then the gas will move faster and the separation would be different, for example, from what they did in the reference books, because we want to compare retention times that we got in our experiment with retention times in data booklets. So they have to be similar. And so the conditions should also be similar. If in the data booklet they used a certain temperature, then we have to use this same temperature while doing our experiment in order to determine our components in the mixture. Okay. But of course, the temperature should be higher than the melting point of or the boiling point, sorry, of the components, so that always the components, the sample mixture should always be in the gas state. So always the temperature here should be higher than the boiling point of the components. Okay.
Yeah, okay. And for the type of questions they ask, do they tell you to like explain it or what?
Yes, sometimes they would ask to explain how يعني how separation is done in such a thing. They will not ask you to draw anything, but they will ask you about the method of separation itself.
Oh, okay, fine.
Yani what is the mobile phase used? What is the stationary phase used? What is its properties, I mean. They ask about the retention time or the retardation factor. Okay. Now, this is also, we said that in this chromatography also, in gas chromatography also, we use retention times. So this is the time 0. Of course, the components will merge out of this column, depending on 2 factors, depending on their molecular mass and depending on whether they are going to be adsorbed at the surface of the liquid stationary phase or would like to be more soluble in the gas state. So we have 2 factors here, the molecular mass, because the gas can carry or can move the components that have smaller molecular mass more than to move the components that have higher molecular mass. So if you look here at this gas chromatogram, you will find that here we have ethanol, here we have hex 1-ene, here we have heptane. So you see that ethanol has a very small molecular mass compared to others. These are propanone. So ethanol means that it has only 2 carbon atoms, but propanone has 3. Hex 1-ene has 6. Hept has 7. Okay, so it depends on their molecular masses and also depend on whether we are using a polar liquid where the components will be adsorbed on this polar liquid, or else they will be they would like to move with the gas state. Okay. Understand,
Miss, we
Lara?
always use polar substances as the stationary, right?
Not always, whatever you want. You can place it a non-polar or you can place it a polar. It depends.
Oh, fine. Okay.
It depends on your mixture and whether you would like it to be adsorbed on the stationary phase or move with the mobile phase. Okay. Of course,
okay.
the area under the peaks here determines the concentration of each component in the mixture. If we have big area, this means that we have more concentration of pentene to one than we have for example, ethanol. Ethanol came out the first before it came first before pentene 2-one because it has a lower mass. Here we have only 2 carbon atoms and here we have 5 carbon atoms. So depending on the molecular mass, pentene 2-one came later. But also it depends upon whether it will be adsorbed on the stationary phase or not, the sequence of coming out from the detector. And the area under the peak shows us the concentration of each component in the mixture. Okay, so if we want to find out the amount of any component of this, as you see, this resembles a triangle. So we are going to draw a triangle. We are going to draw here a triangle. And from this triangle, we can measure the area of the triangle, half base times height, and we get its concentration or its amount, I mean. Okay. Understand, or shall I repeat anything?
I understand, Miss.
Okay. So here, for example, if you want to get an approximate percentage of Esther A, where is A? As I told you, we calculate the area under the peak by drawing a triangle and calculating half base times height. I don't know what's Esther A, but Here it says the amount of each component in a mixture is found by expressing it as a percentage of the sum of the areas under all the peaks. We calculate all the areas, and then we are going to, for example, if I want to calculate the area under this peak, it is defined as a percentage. So we divide the area of this peak divided by the total areas of all the components times 100, and we get it as a percentage. Now, also GLC is used to test for the steroids in competing athletes, like in HPLC, we can use either this or that. And also to test whether the fuels used in Formula One motor racing also has the same properties that it should have. So they can also use gas liquid chromatography. And also we can determine the percentage of oxygen or nitrogen or carbon dioxide or carbon monoxide in blood samples. Even if the blood sample is very, very small as 1 centimeter cube, we can determine the percentage of the gas particles in it. So GLC and HPLC are widely used, of course. Okay. Do you have any question?
No, miss.
Okay. Now we come to the proton nuclear magnetic resonance, or we call it proton NMR. Now, okay. Either proton NMR, or we are going to talk about in general. Now, in general, inside an atom, we have the nucleus. And that's why they call it nuclear, because it's dealing with nuclei, nuclear magnetic resonance. So it's dealing with nuclei, nucleus. And inside the nucleus, we have protons and we have neutrons. Okay, we have a number of neutrons and we have a number of protons. And scientists say that inside the nucleus, the protons and neutrons are distributed in energy levels exactly like electrons are distributed in outer shells. Okay, it says that protons and neutrons are found in shells inside the nucleus, and that as we used to distribute electrons, for example, we say that we distribute them single electron first and then paired, isn't it? So scientists say that inside the nuclei, protons and neutrons are also distributed in shells in the same way as electrons are distributed. And so we can either have paired protons or neutrons, or we have unpaired proton or neutron. Okay, understand till now?
Yes.
Okay, now if we have the number of neutrons the same as the number of protons, or if we have even number of neutrons and protons, this means that all of them are paired. And this means that if the protons and neutrons are paired inside the nucleus, then we will not get an NMR spectrum, what we call NMR spectrum. We don't get it as long as we have even number of protons inside the nuclei. But if we have odd number of protons, if we have an odd number of protons, so this means that a proton is found unpaired. Of course, when we draw an arrow, it means it's spinning in one direction. Okay, when we draw an arrow, it means spinning, because scientists also said that, as we said about electrons, we said that electrons rotate around orbitals around the nucleus, and at the same time, they spin around itself. Well, while they are moving, they are spinning. You know what's spinning? They are doing like that while they are moving.
Yes.
Okay. So also, scientists said also protons do the same. If they are present inside the nucleus, they are spinning. And if we have an odd number of protons, let's start with a hydrogen atom, It contains only one proton. So this proton is spinning. And whenever we have something spinning, when the proton is spinning, then it creates a magnetic field. It creates a magnetic field. When anything is spinning, it creates a magnetic field. Okay. Now, in NMR spectroscopy, we place our molecule in between two magnets. This is the North Pole and the South Pole of a magnet. And of course, the magnet has an external magnetic field. The magnet possesses a magnetic field that we call it the external magnetic field. Now, if our molecule here contains a proton, and we said that this proton would spin around itself, and spinning would create a magnetic field. So if we place it in between the two poles of a magnet, then either the magnetic field produced by spinning of the proton is aligned with the magnetic field that is produced from the magnet. Then here we have two cases. Either the magnetic field produced from the proton is aligned with the external magnetic field of the magnet, or else it is opposite to it or opposing it. Okay, so inside any nucleus we have protons. If we have odd number of protons, this means that at least one of the protons is unpaired. And this unpaired electron spins. And on doing so, it creates a magnetic field. And if we place our compound containing this proton in an external magnetic field, so one of two things would happen. Either the spinning of this proton produces a magnetic field that is aligned with the magnetic field produced by the magnet, or else opposing it. Either it produces a magnetic field that is aligned with, it means in the same direction as the magnetic field of the magnet, or else it would produce a magnetic field that is opposite to the magnetic field of the magnet. Okay, Laura?
Miss, shouldn't it be, if it aligns with it, shouldn't it be from left to right? I mean, right to left?
I mean that we draw the arrows in this way means aligned with. And if we draw it in the opposite direction means it is opposing it. I know that the magnetic field passes from north to south here like that. But we represent aligned with in this direction, and we represent opposing it in the other direction.
Oh, okay.
Okay. Now, inside the molecule, we have many protons, not only one. We have many protons. And so we have a number of protons that will create a magnetic field that is aligned with the magnetic field. And we have other protons that would create a magnetic field that is opposing to a magnetic field. And those that are opposing the magnetic field would be at a higher energy level, than those that are aligned with or produces a magnetic field that is aligned with the external magnetic field. Okay. Okay, Laura, or do you have anything you would like to ask about?
Okay, I understand.
Okay. Now, if this molecule is not only subjected to the magnet, but also subjected to light energy in the radio frequency, which is, of course, it's a very small energy. So in that case, the protons that are present in the lower energy level will absorb this amount of energy, which is the radio frequency, and be promoted to an upper higher energy level. And on doing so, it will produce a peak in the magnetic spectrum. Okay. Understand?
Miss, can you repeat the part about radio frequency?
If we subject our molecule that is present, that contains unpaired number of protons, and at the same time is present in between the two poles of the magnet, if we subject it to a radio frequency, which is a small amount of energy, you know, radio frequency is before the microwaves. You know,
yes, radio
the division. Yes, radio frequency. So the protons would absorb the energy of this radio frequency and be transferred from the ground state to the excited state. And on doing so, they produce a peak, or this one, in our NMR spectroscopy.
Yes, okay.
So it depends on the number of protons. It depends on two things: the number of protons and their environment. Depending on the environment, what do you mean by the environment? For example, if I have a molecule like this, CH3, CH2OH, we say that we have 3 different proton environments, because every hydrogen, its place is different from the other. This hydrogen is bonded to an oxygen, and these 2 hydrogens are bonded from one side to an oxygen and from the other side to another carbon. And these hydrogens are bonded to a carbon that is bonded to only one carbon atom. So these 3 hydrogens differ. They are placed in a different environment than these 2 hydrogens, which is also present in a different environment than that proton. So depending on their environment, the peaks will appear. Some of the peaks will be in a place that is different than others. Of course, we are going to see now how this NMR spectrum is labeled. Okay, but if we have 3 environments here, it means 3 different positions for the hydrogens. This means that we are going to get 3 peaks. Every environment of hydrogen would give me a peak in the NMR spectrum. And depending on the number of protons that it has, if it has 1 proton, it will have only a small peak like this, a small area below the peak. If it has, for example, 3 protons, it will have a peak that is bigger than if we have 2 protons.
So, Miss, like CH3 would have the highest peak.
Yes, it will have the highest peak because it contains 3 hydrogens. They are going to write for us how many hydrogens does this represent, this area represent. Okay?
Yes, okay.
Understand till now?
Yeah, understood.
Okay. Now, as we said that we must have odd number of protons in order that we get the NMR spectrum. So only we are going to study 2 types of atoms that have odd number of protons, which are the proton itself, the hydrogen itself, we call it proton here, and the carbon-13. In the carbon-13, not the carbon-12. The carbon-12 has 6 protons and 6 neutrons. But in case of carbon-13, we have 6 protons and 7 neutrons, which means that only 1 neutron will be subjected to the NMR spectroscopy. We have an odd number of either protons or neutrons. So we are going to study the NMR spectrum of the protons and of carbon-13.
Miss, I don't get why you put carbon-13.
because we know that carbon has three isotopes: carbon 612, carbon 613, and there is another one which is carbon 614, but this one is present in the upper atmosphere, not in our lower atmosphere. Okay, so these are the carbon isotopes that are present in our normal atmosphere. But the carbon 12 is present in a high percentage, about 98%, and this about 1% or 1 point something percent. Okay. So here we have in the carbon 612, we have 6 protons and we have 6 neutrons. So they are even numbers, and even numbers, we said that they do not contribute in the NMR spectroscopy. They must be an odd number.
Oh, yeah. And 7 neutrons per
yes, here we have 7 neutrons. It means that 6 protons will go with 6 of the neutrons, and we are left with only 1 neutron. That is an odd number, and this means that it can absorb and it can form an NMR spectroscopy.
Yeah, okay, fine.
Okay, now we said that when we have something alone, it's odd number, it will start to spin, and due to this spinning, it will create a magnetic field. And if we place it in an external magnetic field, then we will have some of the protons will rotate in a way that would be aligned with the external magnetic field, and others would spin so that they create a magnetic field that opposes or against the external magnetic field. And there is a difference between their energies. It's a small difference, but it's present. Okay, so if this molecule containing these protons or neutrons are placed in subjected to radio frequency waves, then this proton would absorb this energy and be promoted to the higher energy shell, and on doing so, it gives us a peak in the NMR spectroscopy. Okay. Now, of course, everything must have a reference. What is our reference here? Our reference here is a substance that is called tetramethylsilane. TMS means tetramethylsilane. It means that we have silicon that is bonded to 4 methyl groups. Tetramethylsilane. And they have chosen this, this compound to be the reference because it contains 12 hydrogen atoms around the silicon. Of course, this is a very big number, so it will produce a single. Of course, also, all of the hydrogens are in the same environment because all of them are bonded to a carbon that is bonded to a silicon. So we have 12 protons that are present in the same environment, so they give only one single peak, and it's a high peak, and we are going to consider this peak to be our reference, which is the tetramethylsilane. We are going to take it as the 0. And any other peak will appear here on the right, on the left-hand side of this peak, and our units here, or our graduation here, is called the chemical shift. How much is it shifted from the 0 point? We call it the chemical shift, and it has this symbol, which is the delta. And we write part per million. Its units is part per million. Okay. As that's what I was explaining to you. Either the nucleus would spin in one direction or would spin to the other direction. And this is the direction of the magnetic field applied. So some of the nuclei would rotate in a manner to produce a magnetic field that is aligned with the external magnetic field, goes through the external magnetic field. And we have other nuclei on spinning, they produce a magnetic field that opposes, that is opposite to the magnetic field applied by the external magnetic field. Okay, Lara, understand? That's what I was explaining for you.
Yeah, okay. Miss, we have to know from left to right or right to left, or no need? Because here it's
Where is
always
the
the against.
Yes.
Like the against part, the arrow is going like clockwise.
Here it's moving anti-clockwise, and here it is moving clockwise. They are not going to let you do anything like that. In your course, we are going to be asked about the spectrum itself. I didn't see in any exam paper they are asking about how is NMR spectrum produced. I didn't see that, but we have to know what is NMR before we start dealing with it. Because if I started at once to tell you about the peaks, you will ask me from where did these peaks come from and what are they, and you are going to be asking. That's why they give you a small introduction in order to know what is proton NMR or carbon-13 NMR before we study the spectra itself. Okay?
Yes,
but of course, we have to know that our reference is tetramethylsilane. This is our standard, and any other peak will come to the left of this 0 point. In chemical shift, we put delta, and its units is part per million, ppm. Okay. You see, these are the peaks that come from an NMR spectroscopy. We draw absorption of energy against absorption, of course, of the radio frequency that I told you about against the chemical shift. We call it delta in parts per million. When we have 3 peaks like this means that we have 3 different environments for the hydrogens. Of course, this is of ethanol. Here we have 3 different environments for hydrogens. It means that every hydrogen is bonded to a carbon or bonded to an oxygen that is different than the other. So these 3 hydrogens together, they are symmetrical, they are equivalent. So the 3 of them will get only 1 peak here corresponding to 3 hydrogen atoms. And the other 2 hydrogens, these 2 hydrogens are similar, and they are at a different environment than the first. That's why we get them in a different place corresponding to 2 protons. And the last hydrogen here is bonded only to an oxygen, so it appears alone as a 1 hydrogen. The area under the peak corresponds to 1 hydrogen or 2 hydrogens or 3 hydrogens or whatever. Okay. Now, as I told you, every peak appears at a different chemical shift depending on its environment, depending on when it absorbs the radio frequency. It will be its protons will be, or neutrons will be transmitted from the ground state to the excited state. So there are ranges, there are different ranges. They don't appear at anywhere. No. We have a table in the data booklet that shows us if we have a CH3 group, then it will appear in the proton NMR spectrum in the range from 0.7 to 1.66 part per million. It will appear in this range if we have a CH3 that is bonded to CH2, like in this example. If we have a CH2 that is bonded to an OH or to an oxygen, then it appears in the range from 3.3 to 4.3, like this one. If we have an OH, then the hydrogen is bonded to an oxygen, it will appear in the range of 5.4 parts per million. So you have a table in your data booklet that shows you every species would be present at which part as a chemical shift in part per million. Do you have a data booklet now?
Yeah, Miss, it's already opened.
So you can open it on the part that is talking about the proton NMR spectroscopy, and you will see that there is a table that shows us if we have a CH3 bonded to another carbon, then its hydrogens would appear in this place. If we have hydrogens that are bonded to a carbon bonded to an oxygen, they appear in that place. There is a range. Okay, this is the table. Okay, and you see the table?
Yes.
Okay, it shows us that if we have a CH3 bonded to an R, we said before that R means a carbon. It's either it's one carbon or two or three or others. So here, if we have a CH3 that is bonded to a carbon, then the hydrogens of this CH3 would appear in the range between, at the chemical shift between 0.7 to 1.6 parts per million. If we have a hydrogen that is bonded to a nitrogen, or a hydrogen that is bonded to an oxygen, it would appear in the chemical shift from 1 to 5.5. Okay, now here they are writing A because they say that hydrogens that are bonded either to an oxygen or to a nitrogen, they have variable chemical shifts depending on our molecules. But of course, for you, they are going to place it in a certain value that is here between 1 and 5.5. If we have hydrogens bonded to a carbon that is bonded to two other carbons from both sides, then these hydrogens would appear in the chemical shift between 1.2 to 1.4. If we have a hydrogen that is bonded to a carbon that is bonded to three other carbon atoms, it will appear in this range, and so on. If we have a hydrogen that is bonded to a carbon bonded to a C double bond O, then this hydrogen would appear between 2 to 2.9, or if it is bonded to a carbon that is bonded to a C double bond O from one side and an R group from the other, then all of these will appear in this range. Understand me? If we have a benzene ring and we have hydrogens bonded to a carbon that is bonded to a benzene ring, then it will appear between 2.3 to 2.7.
Miss, for like in my data booklet, it's not like the same. It's, I don't know why it's different.
You mean the numbers, or what do you mean?
Yeah, like the numbers and the way they wrote it is different. Like they don't.
Yes, okay, the way they wrote is different. It's okay, because of course every reference would put the way it's writing its data in a different way, but the chemical shifts are nearly equal, or maybe nearly the same. Are they different? Completely different?
Miss, like for example, for the one about CH3 bonded to R, yes, the first one.
Yes.
The chemical shift that shows me is 0.9 to 1.7.
Yes, okay, so you are going to from 0.9 to 1.7, so it's nearly in the same range. Here they wrote here from 0.7 to 1.6, it's nearly the same. My data booklet is an old one, it's writing only 0.9, it didn't put a range. But you are going to use your data booklet. You are not going to use this book. You are going to use your data booklet, so you are going to give the examples from your data booklet, because sometimes they write you to put the numbers, to put the chemical shifts of each peak that appears. So you have to take from your data booklet. Okay. If you have a benzene ring, then the hydrogens in the benzene ring appear in the chemical shift from 6.5 to 8. In my data booklet, it's written 7.3. It's in between 6.5 to 8. Okay, so you will adhere to your data booklet. Okay, Lara? Understand what I mean?
Yes, Miss.
Okay. Now we said that, for example, if we have something like ethanol, then at the beginning, we are going to see how many environments are there for hydrogen, from which we can expect how many peaks to obtain. And from the values of these peaks, we can also determine what are these peaks, what do they represent. And we call this the low resolution NMR spectrum, low resolution, okay? But we have another type of NMR spectrum that we call it high resolution NMR spectrum. Now, what is the high resolution NMR? High resolution says that if I have, for example, like we had here, CH3 bonded to a CH2 bonded to an OH, we said that this is an environment, these two are a second environment, they are similar, and these three are a third environment. All of them are equivalent. Okay, so here we have three different environments. But in high resolution NMR, it says that it's a type of course of NMR spectroscopy. In this spectroscopy, we will find that these hydrogens that are equivalent and present on this carbon will be affected by their adjacent hydrogens or their neighbor hydrogens. They are affected by them. And these hydrogens are also affected by the hydrogens, these three. They are affected. But this hydrogen, it is not directly attached to a carbon that is bonded to other hydrogens. It is bonded to an oxygen. And the oxygen then is bonded to a carbon. So there is a big distance between this proton and these protons. And that's why it will not be affected by them. So whenever we have two carbon atoms directly attached to each other or adjacent to each other, and each one of them carrying a number of hydrogen atoms, then these protons will be affected by the protons that are neighbors to them, and these protons are affected by their neighbor protons. How are they going to be affected? We will find that each of these peaks that we have drawn before, we have drawn, this is the OH, we have the CH2, and we have the CH3. We will find that every one of these peaks, this was OH, the hydrogen of the OH, this was the hydrogens of the CH2, and this peak represented the three hydrogens of the CH3. We will find that each one of these will be splitted. We call them splitted into a number of peaks. So the OH, we said that this hydrogen is not going to be affected by other hydrogens, so it will appear as only one peak like that. But we will find that the CH2 will appear as four peaks. The CH3 is going to appear in the form of four peaks in the ratio 1 to 3 to 3 to 1. And these three hydrogens that are next to the CH2 will appear in three peaks. They will be formed in three peaks. They will be split into three peaks because there is a rule that says that the splitting caused depends on the number of hydrogen atoms that are adjacent to it, to the first one. And the peaks are going to be splitted by the rule n+1. It means that here, these two hydrogens are adjacent to three. They are affected by these three. And so the peak of these two hydrogens will be split into four. Why four? Because here we have three hydrogen atoms. So 3 + 1 makes four peaks. So this peak is going to be split into four because it lies next to a carbon that is bonded to three hydrogen atoms. And in a similar way, these three protons in the low resolution NMR spectrum, they appeared as one peak, but they are going to be split into three because beside them, we have two protons. So 2 + 1 makes 3. We call this the high resolution NMR. Okay, Lara, you understand?
Yes, Miss.
Okay. So here, this is the CH3, CH2OH. We will find that this peak is split into three because we have two protons next to it. And this one is split into 4 because it has 3 protons next to it, while this proton is not split at all, depending on the rule n+1 rule. Okay.
Yes, I understand.
Okay. When we have number of adjacent hydrogen atoms 0, like the OH, then it will appear as one peak, and we call it singlet, a singlet peak. Okay. If we have the number of adjacent hydrogen atoms is 1, then the peak will be split into 2, and +1 means 1 + 1, 2. So we get 2 peaks, we call it doublet, and it will appear in the ratio 1:1. If we have the adjacent number of hydrogen atoms is 2, then the peak will be split according to the rule n+1, 2 + 1 makes 3. 3 peaks, we call it triplet, and we get a triplet peak in the ratio 1:2:1. And if we have number of adjacent atoms 3, then our peak will be split into 4. We call it quartet. It will be in the ratio 1:3 to 3:1. We have to know the ratios. Okay.
Okay, fine.
Okay, for example, here it says an ester is used as a solvent in a glue. A chemist was given a sample of the ester to analyze. The NMR spectrum of the ester is shown. This is the high resolution NMR spectrum of an unknown ester in a glue. Identify possibilities for the 3 major peaks that appear at chemical shifts 1.3, 1.9, and 4.1 part per million using the table, of course. Now, we look here, we find that we have 3 environments. At the beginning, we have 3 different environments. And this means that we have different environments, 3 different environments for the hydrogens in this ester. Okay. Now, here it said that this peak corresponds to 3 hydrogens. This peak also corresponds to 3 hydrogens. And this one corresponds to 2 hydrogens. Now, we will see that this one is split into 3, and this means that it was adjacent to CH2. Okay, from the beginning, we say that this is split into 3. This means that, yes, it was a CH3, because they said here it corresponds to 3 hydrogens. So it is a CH3, but since it is split into 3, this means that it is adjacent to CH2, where this CH2 affected it and split it into 3. And this part corresponds to 2 hydrogens. It means that we have a CH2. And since it is split into 4, this means that its neighbor contained 3 hydrogens. Okay. Understand, Lara, till now?
Yes, miss.
Okay, now here we have also 3 hydrogens, but they appear singlet. It means that they are not bonded to a carbon that is carrying hydrogens. It doesn't have any hydrogen neighbors. And here it's stated that it is an ester. So it could be like that. It could be like that. CH3, these 3 hydrogens do not have a neighbor hydrogens beside them. That's why the 3 hydrogens appeared as a singlet. So it could be, this ester could be in this way. Okay.
Miss, can it be the C double bond O like in from the CH2, then
Yes.
C double bond?
Yes, that's what I was going to tell you, that it could have this formula. Yeah. So who will tell us whether it is this or that? It will be the position of these peaks. Here we said that the CH3 that is bonded to the CH2 appears here. Of course, if it is bonded CH3 to a CH2, then it should appear between the 0 and or 0.9 to 1 point something. But the position of these two hydrogens, either it is bonded to an oxygen or bonded to a C double bond O, this will appear from the table. Now here it is about 4, isn't it? So we will look here at the table. I will look at the table and see 4. Where is 4? These are not here. This is an ROH or ROOH. It means that we have an alcohol, so it's not that one. We have to find out a carbon that is bonded to an oxygen or a carbon that is bonded to a C double bond.
OCH2R.
O, where is it?
It's from 3.3 to 4.3.
3.3. If we have here a CH2 that is bonded directly to a C double bond O, like here, you see, CH2 bonded to a C double bond O, you see this?
Yeah, miss, but we would have
but
4.
Yes, I'm just showing you. It would appear between 2 and 2.9.
Yeah.
If I have a CH2, you see this is the bold hydrogen, this is the one that we are talking about. If we had the CH2 bonded to a C double bond O, then it would appear between 2 and 2.9. But we don't have this value, we have it at 4. Okay,
yeah.
So where is the other one that you are talking about?
Miss, the 3.3 to 4.3, just
this one? Yes,
yeah.
Yes, excellent. So here we have the CH or the CH2 bonded to an oxygen and to an R group from the other side, to a carbon from the other side. It would appear in this range, and that's what we got. And this means that our compound is the first one, not the second. Now let's find this, the one that appeared as singlet. CH3 bonded to a C double bond O, it appears here. CH3 bonded to a C double bond O. It appears between 2 and 2.9, isn't it?
Yeah.
So if we look at our proton NMR, we will find it to appear at 9, at 2 exactly. So this is the CH3 bonded to the C double bond O. Okay, understand now what are we going to do?
Yeah, it makes sense.
Okay, let's have another example. A pathologist was given a sample of white tablet found at the scene of a suicide. In order to complete her report, the pathologist received an NMR spectrum of the sample and information from the police that the tablets involved were either aspirin or paracetamol. This is aspirin and this is paracetamol. The displayed formulae of both drugs are shown in figure 2920. Using this information, which drug was the white tablet, and explain your answer. Now, we would look at the structures of aspirin and paracetamol. We will find that in both aspirin and paracetamol, we have a CH3 that is bonded to a C double bond O. But here we have an NH, and here we don't have an OH even. Okay?
Yeah.
Here we have an OH in this place. So we have an OH and we have an NH. And here we have a C double bond OOH. Now we got this NMR spectrum. We got a singlet peak that corresponds to 3 hydrogens. And this means that these 3 hydrogens are alone. They are not adjacent to a neighbor carbon-carrying hydrogens. Okay?
Yeah.
So in both of them, we have this CH3 bonded to a C double bond O, and also CH3 bonded to a C double bond O. And if you remember from the previous example, we had it at chemical shift equal 2. So this is the CH3 that is bonded to the C double bond O. Okay. Now, how many environments do we have? At the beginning, we usually count the number of environments. Here we have 1, 2, 3, 4, 5 environments. Now, let's look at these two examples. This is one environment. This hydrogen has an environment, and this hydrogen has a different environment. These two are one environment. So 1, 2, 3, 4, and 5. We have 5 peaks. 1, 2, 3, 4, 5. What about the other? Here we have 1, 2. These two are similar. 3. These two are similar. 4, and this one alone. Also, it has 5 environments. So the first thing to look at is the number of environments. If they are different, so from the beginning, we can deduce which structure. But here, both structures have 5 environments for hydrogen. Okay. Now, we said that this is the CH3 peak. Now, here we have 2 hydrogens that are equivalent. And here we have also 2 hydrogens that are equivalent. And we have 2 hydrogens, each one alone. I think this is the structure. Now, if we look at this, we said that we should have a peak corresponding to this one alone, and for this one alone, and these two are equivalent, and this one alone. Okay, so we would have a peak corresponding to 1 proton, a peak corresponding to 1 proton, and a third peak corresponding to 1 proton, and a peak corresponding to 2 protons. So we should have 3 peaks corresponding to 1 proton. Here we have only 2. Understand what I mean?
Yeah.
But if we look here, we have NH has only 1 proton, and NH has another proton. These 2 protons are similar, so they appear together. These 2 protons are similar, so they appear together. Okay? And every proton is doubled because its neighbor hydrogen contains only 1 hydrogen. So it will affect it by splitting it to a doublet. Okay, Laura, so I think that this is the structure, paracetamol. Is the right one?
Miss, can you repeat the part about the hydrogens?
Yes, if we look here at the aspirin, we will find that this hydrogen should appear alone. Okay. And
yes,
this hydrogen also should appear alone because its environment is different than that environment. This hydrogen is bonded to a carbon that is bonded to C double bond O, but this hydrogen is bonded to a carbon that is bonded to CO, direct CO, not C double bond O. So this environment differs from that one. But these 2 hydrogens are equivalent. They are in the same environment.
Miss, how are they in the same environment? One is bonded to
because both of them is bonded to a carbon that is bonded to a CH, bonded to a carbon that is bonded to a CH. So together they are equivalent. We look at their direct neighbors.
Oh, Miss, I thought you look at the, not just the neighbor, the one also like after, like everything.
No, here it's bonded to a carbon. This is its neighbor that is bonded to a C double bond O. This is its direct neighbor. As here, we took its direct neighbor. Understand?
So we only look at the direct neighbor.
Yes, mostly.
Okay.
So it will have a peak corresponding to 2 hydrogens, for example, but we have 3 peaks that should be every one singlet. But here we have only 2. This means that this structure is not correct. But here we have an NH. This means that this is a singlet. OH, it's another singlet. And these two hydrogens are equivalent. They are bonded from both sides like the same. And these two hydrogens are equivalent. They are bonded from both sides the same. So we have here two peaks, one of them corresponding to two hydrogens and the other corresponding to other two hydrogens. Okay, Laura. So the first thing to notice, the number of peaks and the number of environments. If they are equal, then we start to see each peak corresponds to how many protons. And then we see the splitting. And we see the chemical shift of each, because right now we do not know which one of them is the, of course, the NH and the OH both appear in the same place, but here the N is bonded to a C double bond O. So I'm going to see, will it affect if I have an NH bonded to a C double bond O? You see, it will appear between 5 and 12. It's a wide range between 5 and 12. And the OH, we had an OH bonded to a ring. It's something like that. So also it appears between 4.5 and 10. This is between 4.5 and 10, and this is between 5 and 12. And this means that one of them, we don't know which one of them. This will be an NH, and the other will be an OH. We don't know which is which. Okay. Understand, Lara, or shall I repeat it?
Miss, I don't get the part of why it's 2H on the double peak, the doublet.
Why is it doublet? Why is this a doublet?
No, Miss, why it's written on it 2H?
Why is it written 2H? Why is it written 2H? Because I told you that these are two H's in the same environment. These two H's are in the same environment. This one and that one. Both of them are bonded to a carbon that from one side is bonded to a CO and from the other is bonded to CH. This is bonded to a CO and from the other side to the CH. So these two hydrogens are equivalent. They should have only one peak, but this peak is doubled because it is a neighbor to another CH. This H will split this H in a doublet, N plus one peak. Understand?
Like, Miss, for example, in the case of TMS, the one about tetramethyl, whatever, in this case, when we had four CH3s, they were all in the same environment. The H was in the same environment. So here in this case, like, how would we draw it? Would we draw like 4 and each would be doublet or what?
No, for why 4? These two hydrogens are equivalent. You know what's equivalent? They are similar. Why are they similar? Because every one of them is bonded to a carbon that is bonded from one side to a CH and from the other side to an OH, isn't it? The other is similar to it. It's bonded to a carbon that is bonded to COH and from the other to CH. So both are in the same environment. At the low resolution, they would appear as only one peak corresponding to 2 protons in the low resolution. Understand? But here it was doubled. It was doubled. Why? Because every one of them is a neighbor to another CH. This H will split this one by an N plus 1 peak. So 1 plus 1 makes 2. It will appear as a doublet.
Oh, so it's because of their neighboring carbon had an H.
Yes. Because its neighbor has an H. So this H will double the peak of these two H's according to the rule N plus 1. But if we were dealing with the low resolution NMR, both of them will appear as a singlet peak corresponding to 2 protons. And these two other protons they are similar because every one of them is bonded to a carbon that is bonded to a CN from one side and to the CH from the other side. The same for here. So these two are similar. They are in the same environment. But they were doubled because every one of them is bonded to a carbon carrying only one H. Its neighbor carbon carries only one H, so it doubles its peak. They appear as doublets.
Yeah, okay, I understand.
Okay. Now, for the OH and the NH signal in the NMR spectrum, in the high resolution NMR spectrum, they appear, as we said, as a single peak. But in order to be sure, because sometimes we have another hydrogen that also appears as a singlet peak, and maybe we will get confused between the OH carrying a hydrogen and a CH that also carries only one hydrogen. So in order also here it says that the peak of the OH is not split by the proton atoms on the neighboring CH2 group. We said that we have a CH2, we have an OH, and we have CH2 here, isn't it? Now, why this is not splitted? I told you because it's not directly bonded to a carbon carrying a hydrogen. And there is another reason here, is that this hydrogen in the OH, this hydrogen of the OH, if placed in water, or even if we have a solvent that contains traces of water, this OH, we will find that it will exchange rapidly with the hydrogen of the water. Now, why does this hydrogen appears as a singlet? As a beginning, it appears as a singlet because it is not bonded directly to a carbon that is bonded to hydrogens. But there is another reason, is that when this OH is present, of the alcohol is present in water, or even if we have traces of water in any solvent, we will find that this H exchange its place with the hydrogen of the water molecule. And this exchange is very rapid. The exchange is very rapid. This hydrogen goes to the water and the hydrogen gives it its hydrogen. And in the next second, they exchange places once more to return as they are. This exchange is caused quickly and during a very small time, so that it will not allow the hydrogens on the neighbor carbon to split it. Understand?
Yes, okay, miss.
Okay. It says that if we have, this is completeness of the table, that if we have a hydrogen that is an alcohol, it appears in this chemical shift from 1 to 5.5. It is, if it is present as in a phenol, it appears between 6.5 to 7. If it's present in a carboxylic acid, the OH itself, it will appear between 11 to 11.7. If it's an NH, it will appear between 1 to 5.5, just like the OH. If it is an amine or an NH2 bonded to an arene, it will appear from 3 to 6. If we have an NH bonded to an amide, it will appear between 5 to 12. Of course, we don't have to know any value of this, only to look at our data booklet to find out the places. Okay. Now, as I told you, sometimes when we have a peak which corresponds to an OH or an NH, and we want to make sure that it is an OH, not a CH, then we are going to use our solvent. We call it deuterated water. deuterated water means that instead of hydrogen in water, we use deuterium. You know, we have H11, we call it proton or protium. And we have the other isomer, H12, we call it deuterium. Okay, and deuterium contains one proton and one neutron, and altogether they are even number, and this means that it will not absorb in the NMR spectroscopy. So if we want to find out whether this OH is an OH or an NH and not a CH, we use deuterated oxide, which is water, but using deuterium instead of hydrogen. And since deuterium has 2 protons and neutrons, it's an even number, it will not absorb in the NMR spectrum. And we will find that if we do our NMR spectrum at the beginning in normal water or in any other solvent containing water, we will get this peak. But if we repeat the NMR spectrum in deuterium oxide, we will find that this peak will not appear. It will disappear. And this will make us sure that this peak was of an OH or an NH and not of a carbon hydrogen. Okay. It means that
Miss, can you repeat?
Yes, we said that if I have a peak corresponding to an OH or an NH, I want to make sure that this is a peak of an OH and not a CH. So we are going to, after taking the proton NMR spectrum in a certain solvent, we are going to repeat the NMR, but in deuterated oxide, in water that has hydrogens in the form of deuterium, not protons. And deuterium contains 2 protons and neutrons. The number of protons plus neutrons equals 2. It's an even number. And this means that it cannot absorb in the NMR spectrum. And we said that this H of the OH exchange places with water, with the hydrogen in the water, isn't it? So if instead of using water, I used deuterium oxide, then the exchange will be such that CH3, CH2, OD plus HDO. So deuterium replaces the hydrogen of the alcohol, and this means that this hydrogen will not appear in the NMR spectrum because it was replaced by a deuterium, which doesn't show a proton NMR. And so this peak that we got it at the beginning before using the deuterium oxide will disappear when using the deuterium oxide. Understand, or shall I repeat it?
Miss, deuterium has 2 protons?
No. Deuterium has, this is deuterium. You see here up on the upper left here?
Yes.
This is deuterium. It's hydrogen containing, it's an isotope of hydrogen, 1, 2. It means that it has protons plus neutrons equals 2, an even number. And at the beginning, from the beginning, Khalis, I told you that NMR does not have any peaks for what has an even number of protons and neutrons. They must be odd. That's why we did proton NMR and not deuterium NMR.
Yes, but you didn't say the sum of the protons and neutrons. You said the protons and neutrons should be odd in order to get the NMR.
Yes, the sum of them. The sum of them should be odd.
So the sum?
Yes, that's what I told you about carbon 13. When I said about carbon 13, I said that carbon 12 has 6 protons and 6 neutrons. And here for carbon 613, we have 6 protons and 7 neutrons. So 7 protons will be even with another, 6 protons will be even with another 6 neutrons. And we are left with 1 neutron that can absorb in the NMR spectrum. isn't it?
Yeah, miss, I just thought of it as here we have one proton and one neutron.
Where?
So they just cancel out.
In proton or where? Or here?
In deuterium.
No, deuterium, we have one proton and one neutron. So together they are paired. And this means that they cancel and they will not absorb in the NMR.
Oh, so we just look at the mass number in the end.
Yes.
So we look at the mass number, and if it's even or odd, depending on that, it will show.
Yes. But you are not going to study except carbon-13 and proton only.
Okay, miss, and so here, since deuterium we got, it's not gonna show in the spectrum. So then after that, here when we reacted it with the OH or the NH signal, it will take the place of the hydrogen, and after that, the peak will disappear because deuterium is aslan doesn't show.
Yes, that's what I'm saying, yes. So if we take the NMR spectrum at the beginning, we got an OH peak. So we repeat the experiment in deuterated oxide, D2O. We will find that this peak disappears. So this will make us sure that this was an OH peak or an NH peak.
And miss, when we did it in water, this one, it showed a peak or what?
Yes, it shows the peak, yes. Because but we only say that it is not splitted. It is not splitted because the proton is exchanging with the proton of the alcohol is exchanging with the proton in the water.
Yeah.
That's why it is not splitted. It appears always as a singlet.
Oh, but for in the case of deuterium, it's gonna make the singlet disappear?
Yes.
Okay, fine.
Okay. Now we have another type of spectrum that we call it the carbon-13 NMR spectroscopy. And in the carbon-13, we just are going to find out in our compound how many environment for carbons this time, not for hydrogens. Also, if I have here, for example, CH3, CH2OH, this means that I have only 2 carbon environments. If I have CH, and here I have CH3, CH3, and another CH3, this means that I have 2 carbon environments. This one, all these are similar, and this is a second one. So now we are going to search in carbon-13 NMR spectroscopy, we are going to search for the different environments of carbon atoms. Okay.
Yes, okay.
And also, we are going to have a table that will show us the different environments of the carbon-13. This one shows us that if the carbon is bonded to a hydrogen in an alkyl group, alkyl means that the carbon is bonded to 4 other carbon atoms, 4 other atoms, or it's making 4 bonds in a CH3 or CH2 or CH, then it will appear between 0 to 50 part per million. If it is the carbon is next to a benzene ring or next to a double bond, it will appear between 10 to 40. If it's next to a carbonyl group or a carboxyl group, it appears between 25 and 50. If it is a benzene ring, it will appear between 110 ila 160. If it is bonded to a triple bond N, it will appear between 100 and 25. So we have different environments for the carbon, and just we are going to look at our NMR spectrum, carbon-13 NMR spectrum, and deduce our structure. For example, it says here that we have 2 carbon-13 NMR spectrum, one of them corresponding to a ketone, which is propanone, and the other 2 C6H5, CH2, CH2. Which one of them is this and which one is that? So here we look at in propanone, CH3, C double bond O, CH3. We have how many environments of carbon?
Yes, we have 2 environments.
Yes, excellent. We have this environment, both are similar, and this a second. That's why here we got 2 peaks. One of them at 200 something and the other at about 30. Okay, 30 and, sorry, 30 part per million and about 200 something. If we look at the other one, which is benzene ring bonded to a CH2 and a CH3, we have how many environments? We have 1, 2, we have these 2 are similar. These 2 are similar.
5.
And 1, 2, 3, 4. No, we have these 2 are similar. These 2 are similar, and this is another one. And we have here another carbon.
So 6?
It said that the carbon atoms in the benzene ring are almost equivalent, but will be affected to slightly different extents. You see here, we have here, this is not only 1 peak. This is about 3 peaks, but they are over each other. You see, these are 3 peaks, but are very near to each other. These are 3, 4, 5, 6.
Yeah.
But since they are nearly equivalent, that's why they appeared, you see, these are 3 peaks, but are very close to each other because the carbon atoms are almost equivalent. These 4, maybe, are almost equivalent, except this one. This one is that, and we have a CH2 and the CH3. And of course, from the positions, we can determine which one is the CH2 and which one is the CH3. Understand? We look at in the table. It says that if I have a CH3 bonded to a C double bond O, CH3, this one, R means CH2 or CH3 bonded to a C double bond O, this one. It appears between 25 to 50. It showed here to be 30 part per million. Okay. And the C double bond O itself of a ketone, this is a ketone, appears between 190 to 220. It appeared for us at 220, I think, or was it 200 only? I don't remember. About 200, so it's in the same range. For the benzene ring, it appears between 110 to 160. If we have a CH3 or a CH2, it will appear between 0 and 50. We got it at 25. Here we have a CH2 bonded to a carbon that is bonded to 2 other carbon atoms.
This for the CH2 bonded to the benzene ring, can it be the second one 10 to 40?
10 to 40, yes, because we have a CH2 bonded to a benzene ring, yes. It is between all of them from 0 to 40 in this range. Okay, understand? We look at our spectrum and we look at the table and determine which one corresponds to which one.
Yeah, okay.
Okay, this is all about proton NMR. And then we should take the mass spectrometry, inshallah, next time. Okay. And of course, if we have a chlorine or a bromine, how are we going to get our mass spectrum? Okay, Lara? Okay, but please,
Okay, miss.
I'm sorry that every time I must say this. I wanted you to do it without being asking every time, because now you finished your the fees that you gave me in this class. So please determine how many classes are left. You need them to take them with me, and please tell your mama to pay for them, please. Okay.
Miss, she did not pay when I told you?
She paid, but she paid for only one extra class for this one. She paid
okay.
because we took, before I asked you, we had 2 classes together, and then we took 2 classes together on Friday, isn't it? She paid on Friday morning. She paid for 5 classes.
Yes.
So 2 where we took them before, and then we took 2 on Friday, and this one, this is the 5th. And she paid for
okay,
5
fine.
classes. Okay. Okay, Lara. Thank you so much. See you
Thank you,
inshallah
miss.
next time. You're welcome. Bye.